Hello everyone, welcome back to Code Bits and Bytes, where we break the technology one bit at a time. Today, we are diving into one of the most fundamental questions that every programmer should know. What is computer problem and how do we break it down into bits? Now, when we talk about computer problems, we don't mean our computer won't start or our screen is frozen. We are talking about those problems that can be solved using precise step-by-step instructions. Those steps that eventually can become code. Just like humans use different languages to communicate with each other, likewise, programmers use different programming languages to communicate with machines. Now here's a twist. To effectively communicate with machines, we need to understand how it thinks, what it can process, and how it executes instructions, and finally, how it arrives at a solution. From something as simple as finding the larger of two numbers or creating a chatting app like WhatsApp, to something as complex as plotting the shortest route for a rocket to Mars. Now, these all are computer problems. And here is an interesting fact. Now, a single problem can have multiple solutions, which means different ways to write a code and to solve it. But before we dive into how to approach solving a computer problem, let's take some moments to get familiar with few key terms that we'll hear all the time. These terms might sound fancy, but trust me, these are not. Once we get the concept, these are super helpful. Now, what is program? A program is a set of instructions written in a language that a computer understands. We write these instructions to tell the computer exactly what to do step by step. That could be anything as we discussed before, like adding two numbers, finding which number is larger, sorting a list, or even running a space simulation. So, when someone says, "I wrote a program," what they really mean is that they gave a clear list of steps to follow in order to solve a problem. And guess what? Those steps are called, yes, an algorithm. So our next key term is, what is an algorithm? An algorithm is just a step-by-step plan to solve a problem. It's like a recipe. You follow a series of instructions and at the end you get a result. Every program we write is basically our algorithm written in code. As we discussed earlier, a single problem can have multiple solutions, which means different ways to code it. And each of that code is just a different algorithm. Now, some algorithm might be fast, some slow, some might take more memory, some less. And this leads us to our next key concept, which is complexity of an algorithm. The complexity of an algorithm tells us how fast or efficient it is. For example, finding the larger of two numbers is simple and quick. But what if we had to find the largest number in a list of million numbers? Or even crazier, find the shortest route from Earth to the nearest galaxy, taking into account fuel stops on different planets. And that's where things get interesting, because these kind of problems need more powerful, optimized algorithms. Now, we won't go deep into this just yet. We first need to understand how to break down a problem into smaller bits. Now that we know what a computer problem is, and we have also talked about programs, algorithms, and their complexity. Now let's get into the real fun. How do we actually solve a computer problem? Now, if you are new to the programming language, this might sound intimidating, but trust me, it's not. You just need to think like a problem solver, not like a walking syntax machine. A common mistake we beginners make is we learn a new programming language and directly jump into coding without fully understanding the problem. but that's like trying to solve a puzzle without even looking at the picture on the box. You might make progress, but you will probably end up solving the wrong thing or missing the parts. Before you write a code, pause and ask yourself, what exactly is the problem asking for? What kind of inputs and outputs are involved? Can we do a quick dry run, either in our head or on paper? Also, try to spot any edge cases early. We don't have to go super deep right now, but just being aware of them will save us later. Let's try one example together. Find the largest number in a list. Now pause the video, take out paper and try to do a quick dry run by formulating a solution in your mind without thinking of code or any programming language. Here's what our brain probably did. We scanned each number in the list. We mentally kept track of the biggest number we had seen so far. Perfect. That's our logic at work. Now let's formalize this. It is one of the most powerful skills we can build. This is where we turn our thought process into manageable sub-problems. And now this technique is called problem decomposition. And it's exactly how software engineers tackle to solve massive complex problems. For our example, how long is the list? How do we compare numbers? What if the list has only one number? And what if the largest numbers appear more than once? Now we'll answer all those questions one at a time, like connecting puzzle pieces. And for now, let's assume the list has 10 distinct numbers. We'll handle more complex versions later. To track the largest number, we just need a simple rule. Start with the first number as your current largest. Compare the current largest with the next number. If a number is larger than your current largest, remember it, replace it. Done? Simple and solid. This is the most underrated step, but will also save us a lot of hours of frustration. So before writing the code, let's try to understand these ways to formulate the solution. Flowchart. It is a visual representation of steps and decisions. Here is an example. Pseudocode. It is about writing steps in plain English or in your own language. Here is an example. Dry run. It is about simulate the logic on paper or in mind and understanding of output on few sample inputs. Input-output table. It is about mapping out sample inputs with their expected outputs in a tabular form. It is similar to dry run, but to detect early special test cases. Now that the logic is clear, it's time to code. Start simple. Write the simplest version of your code and then test it, fix it, and repeat. See, this is the continuous process. Your code evolved and gets better after different series of testing sessions on different inputs. And don't worry about writing perfect code right away. Even expert developers and software engineers write messy code. What matters is the clarity of solution and improvement. Now this is the last step. Once your code runs, time to stress. Test your solution on different inputs. Try with a normal list, then try with edge cases, like for example an empty list or a list with only one number. Also try with negative numbers, and then try with duplicates. The more you test, the more confident you become, and the more solid your code gets. Once you get used to this process, solving computer problems won't be just easy, it'll actually be fun. And there you have it. You have walked through the core steps of solving a computer problem, from understanding the problem to breaking it down, planning your logic, writing and testing the solution. Now, I would love to hear from you. Which problem solving method did you find more helpful? Was it flowchart, pseudocode, dry run, or maybe input-output table? For me personally, I heavily rely on dry runs and then actually writing the pseudocode. So, write your answers in the comments below. Let's see what works best for other creative minds. If you have enjoyed this video, don't forget to like, comment, and share it with your friend who is just starting their coding journey. And subscribe to the Code Bits and Bytes to build awesomeness. And here's a little sneak peek into our next episode. We'll be diving into how AI is changing the way we solve problems and how we can use AI tools to build better logic, sharpen our problem-solving skills, and even speed up our learning as a programmer. Until then, keep thinking logically, stay curious, and remember, your machine is only as genius as you are. See you in the next one. Bye.